Welcome to this new class. In the last class, we discussed about the range, kernel, and rank and nullity. In this class, we prove a important theorem regarding the rank-nullity theorem, or we have to call this as the Sylvester law. Before proving this theorem, I just start with the example, find the rank and the kernel or nullity. So, let V be T from R4 to R3 be a linear transformation defined by T of V1, V2, V3, V4 into this form. So, first we try to kernel, let us determine the kernel of this linear transformation, and the kernel of this transformation means we take any vectors V1, V2, V4 belongs to the R4, and such that because the definition of this, if we have a kernel of a T is nothing but is equal to, you have a V belongs to the V such that T of V is equal to 0. So, T of V is equal to 0 means T is T of V1, V2, V4 is equal to 0 of a R3. So, we just write T of V1, V2, V3 is equal to this form, and now if this T is defined into this form, so we can write 2 of V1 minus V2 minus 5 V4, and then we have a same is V1 plus V3 minus 2 V4, and the third elements is 3 V1 plus V2 plus 5 V3 and minus 5 V4. Now, this means this is clearly giving into this form, in the form of this. So, we just say that this is clearly giving the form of a we have a 2 times of a V1 minus V2 minus 5 V4 is equal to 0. This is equal to 0, then we have to write it is equal to this V1 plus V3 minus 2. So, we have a V1 plus V3 minus 2 V4 is equal to 0, and then we have a 3 V1 plus V2 plus 5 V3 minus V4 is equal to 0. So, I just take this solve these 2. So, we just take into the form of a any 2 of them we can try to solve this. This is we have to try to solve this first 2. So, this is clearly one of the relation is this, we have a clearly say that we have a V1 plus V3 minus 2 V4 is equal to 0. So, we have a V1 can be written as a minus V3 minus 2 V4 because it is a 4 and 3. So, we can just by these 2 we can say that multiplied by this equation, second equation by 2. So, we get is equal to 2 of V1 plus 2 of V3 minus 4 V4 is equal to 0, and now we have a 2 of V1 minus you have a V2 minus 5 V4 is equal to 0. Then we have to just taking this. So, this is cancel out. So, you have to getting is equal to simply is equal to you have a V2 plus twice V3, and then you have a plus V4 is equal to 0. So, by this equation we can say simply say that is equal to V2 is equal to you have a 2 minus V3 minus V4. So, the elements of this kernel can be written in the form of a, so kernel of a T can be written in the form of a, we have elements of this form. So, this can be written in the form of V1 is equal to we have a minus V3 and minus twice V4, and then V2 is equal to minus twice V3 minus V4, and then we have a V3 and we have a V4 such that this V1, V2, V3 and V4 are the element of a R. Now, this can be written in the form of this V3 we can say minus 1, and then you have a minus 2, and then you have a 1 and 0, and plus you have a V3 is the form of a, you have a V4 is the form of a minus 2, and then you have a minus 1, 0 and 1, and such that you have a V1 this is can be written in the form, sorry, this is V3 and V4. So, V3 and V4 is the element of a R. So, solving this we getting this. Now, we just say that into this form, solving this we get just into this form, and now that means we can say that kernel is kernel of a T is nothing but is equal to, you have to say the span of minus 1 minus 2 1 0, and you have a 2 minus 1 0 1, and then we can say that the span of this, and now clearly these two vectors are linearly independent. So this means they form a basis. So this is minus 1, minus 2 and 1 and 0. Then we have a 2, minus 1, 0 and 1. This is the B is a basis for kernel of T. So this is, we can say that this is basis for kernel of a T, and then the basis there is a 2 element, and we can say that the dimension of kernel of T is equal to 2, and then we can say that is equal to NT, nullity is equal to 2. So in this case we calculate the nullity of this is clearly is equal to 2. Now we try to find the what is the rank. So we just say that what is the rank of this. So RT is the form of this form. We can RT written in the form of this. This can be written in the form of in the form of this form. We can just say that V1, and then this can be written as a 2, 1, and then you have a 3, and then plus you have a V2, then you have a minus 1, and then you have a 0, and then you have a 1, and plus V3 we can have a 0, and then you have a 1, and then you have a 5, and then we have a plus ka V4, and then we have a minus 5, and then you have a minus 2, and then you have a minus 5, such that this element of this form. So this means this we can say that simply that this RT is nothing but is equal to is written in the form of a span of the elements of this. We have a 2, 1, 3, and then you have a minus 1, 0, 1, and then you have a 0, 1 and 5, and then you have a minus 5, and then you have a minus 2, and then you have a minus 5. And now these are the 4 vectors, but our linear transformation is defined clearly. You have a T from R4 to R3. So this means we have a T is defined from R4 to R3. So there is a basis has a 3 element. Every element n plus 1 element is linearly dependent. So this clearly this set is linearly dependent. That means one of the elements of this can be written in the form of a linear combination of any 2 or all of them. If you just check, if we write, we have to just this minus 5, minus 2 and minus 5. This can be written as a minus 2 times of a 2, 1, 3, and plus 1 times of a minus 1, 0 and 1, and this is clearly this can be written into the linear combination of these two vectors. So this means this is the span of this. So we can exclude this vector. So now we can say that the span of we have a now this is equal to 2, 1, 3, and then you have a minus 1, 0, 1, and then we have a 0, 1 and 5. So this can be written into this form. So this is this span is into this form. Now there are the 3 vectors, and now we check is these 3 vectors are linearly independent or dependent. So if we just we check one of the vector, this means this is this can be written in the form into this form. So you just check, we can write 1 by 2 of this. So 3 by 2 plus 1 this like this you have to get take into the this form. So we just check this vector this 0, 1, 5 can be written as a linear combination of these two or not. We have to check this. So we just take into this form. This is clearly, and now we have to this vector. Now this is can be written in the form of this 0, 5, 1 is equal to written into the this form. So this means we can say that clearly these 3 vectors form a linearly dependent. And if these 3 vectors are linearly dependent, then these are the 2 vectors, and these 2 vectors are clearly is linearly independent, because the property any 2 vectors are linearly independent because none of them is a scalar multiple of other. So 2 vectors are linearly dependent. In the case, one can be written as a scalar multiple of the other, or the line is the collinear. So clearly these 2 vectors are linearly independent. So this means the basis of this RT is equal to, simply we say that this element is equal to 2, 1, 3, and then you have a minus 1, 0 and 1. So, these two vectors are in the basis. So, this implies that we can say that the dimension of you have a RT range of a T is equal to 2, and then you can see this means we can say that RT is equal to you have a 2. Now, you see we have a transformation from R4 to we have a R3. Now, clearly see that we have a dimension of RT is equal to 2, and then we have a dimension of kernel of T is also 2, and then if we take a sum of these two, dimension of a RT plus dimension of kernel of a T is giving you have a 2 plus 2 is equal to 4, is the same as a dimension of R to the power 4, and that is equal to our vector space. So, this is not consequence for this example, this is in general true, and that the result is called is a Rank-Nullity theorem or the Sylvester law for this thing. So, this is the theorem. We try to prove this theorem. Let V be T from V to be a linear transformation and V be a finite dimensional. So, we just specify this should be a V should be a finite dimensional vector space. Then range of a T plus dimension of a kernel of a T is the same as a dimension of a vector space V. Okay, so we try to prove this. So, because you know that this means clearly we know that the kernel of a T is a subspace of V, and you know that we have a given and we have a given that V is finite dimensional vector space. So, this implies that this because this is kernel is clearly subspace of a V, and V is a finite dimensional space, that means kernel of T is also finite dimensional because it is a subspace. So, it is a subspace, that means kernel of a T is also is a finite dimensional. If it is a finite dimensional, then there is a basis, and this means we can say that suppose the dimension of kernel of a T is equal to suppose M, and this is the dimension of N, then the element in the basis of this. We also check a dimension of a V is equal to suppose N, where N is greater than equal to M. So, the condition is this dimension of a V is equal to N and dimension of kernel of a T is equal to M. So, this means kernel of a T is equal to this means V is equal to you have a V1, V2 up to Vn. These are the element, and this is a basis for kernel of a T. So, we start the proof into this form. We check because starting from the we try to find, we know that this is this because we have a given this V is a finite dimensional vector space, and now you know that the kernel of this is a subspace of this vector space V. So, is a kernel is a subspace of a vector space V, that means V itself is a, because V is a finite dimensional vector space. So, kernel is a subspace, and subspace is also is a finite dimensional vector space, and though if it is a finite dimension vector space, then there is some dimension is there. So, we assuming that the dimension of this kernel is equal to M, and dimension of a V is equal to, we have to assuming that is equal to N, where N is should be greater than or equal to M. So, if a kernel of a dimension M means there is some element in the basis M element in the basis. So, we just say that we can assuming that this is M vectors V1, V2, Vm is a element in the basis. So, we have to is the element of a basis means these two vectors, this B is a you have a linearly independent, and you have you just say that the span of B is the same of a kernel of a T, and then span of a kernel of a T means we can say that is also the span of a vector space of a V. Okay, so we just using this way, we assuming this clearly. I explain you how this we can just start. So, we just take a basis V1, V2, Vm and be a basis of a kernel of a T. So, kernel of a T dimension of a kernel of a T is equal to M, because, and then we have to since you have a any vector Vi belongs to the kernel of a T by the definition of because kernel of T you know that is equal to V belongs to the V such that T of V is equal to 0 vector. So, we take any vi, so vi belongs to the kernel of a T, then this is all up to I running 1 to m, because this is the basis of this means T of if because is the basis of a kernel. So, V1 is the element of a kernel of a T, V2 and Vm all are the kernel of a T. So, we just say that V of I is the element of a kernel of a T. So, T of I is equal to 0. And now B is a linearly independent in B, this is a because is a basis. So, this is clearly this is a linearly independent in kernel of a T, and if it is a linearly independent in kernel of a T, that means any this any we have a set. So, we have a this is the subset of a dimension of n is a vector space. So, this is kernel of a T, these are linear independent, then also linear independent into a, we can say that in also linear independent into the vector space of a V. So, okay, so now we just try to extend this linearly independent set V1, V2, Vm to the up to the dimension of the vector space, because extend a linear set up to the basis. So, dimension of a vector space means we have to extend this up to the dimension of the our vector space V, and the element of a basis is n. So, we have to extend this B1 to the up to Vn to Bn. Now, now we consider a set, we have to consider a set like this. We have to take a T of m plus 1 and T of V of m plus 2 and so on T of Vn. We consider this set, and now we try to show that this set is a basis, this set A is a basis for range of a T. So, we try to prove that this is the basis for range of a T, and if we successful try to prove that this is the basis for range of a T, means the number of element in the this is clearly you have a n minus m, and this is n minus m. This is nothing but equal to, we can say that dimension of a range of a T. And now we have know that the n can be written in the form of a, we have to just say that we have to write the dimension of range of T plus m, and n we have to assuming that is the dimension of V, and then we have to just say that dimension of range of a T, and m we assuming that the dimension of we assuming that the dimension of kernel of a T. If we succeed to this, we can just say that this is, if we assuming this set, we from here to here this set, if we successfully prove that this is the basis T of this, because you know that T from we have a V to W, so that is a linear map. So, clearly there is a linear map. Then for a Vi belongs to V, we have to T of Vi is nothing but is equal to some Wi, where Wi is the element of a W. So, by this theorem we have report there is a unique representation of a T of Vi is equal to sum of element of this W vector space. Okay. So, we try to prove this set and then consider. So, now we have to consider a set A. This is T of Vm plus 1 up to this is a. Now, we try to show that this set is a basis for RT. So, which prove that it is a basis for RT, and if basis of RT, we have to prove that the span of A is equal to RT, and A is a linearly independent. Now, a span of A is equal to RT, we have to prove that. So, we just know that we start from the span of B1 is equal to V clearly, because V1 we have a V1 is equal to the element of this V1, V2 up to Vm, we have a Vm plus up to Vn, and this is a basis. So, it is a basis means this is a basis for, this is the basis for V. So, if this is the basis for a vector space V, then clearly there is a two condition is hold, this B1 is a linearly independent, and we have to just say that span of this B1 is equal to a generated whole V. Also, there is a one result, if you remember, we can say that if V1 we say that is equal to V1, V2 up to Vn is a span of sorry, I just said that T from V to W is a linear vector linear transformation, T from V to W linear transformation, and we have some V1 V2 span of V1 V2 Vn is equal to, we have just say that is equal to V. Then we have a result is this is a range of a T is nothing but is equal to is a span of T of V1 up to T of Vn. So this result is clearly say that this we have to already prove that, okay, if T from V to W is a linear transformation and span of V1 V2 Vn is equal to V, then the range of a T is nothing but is equal to span of a T of V1 T of V2 and up to T of Vn. So here we have just said that by we have to proving this. So we just know that V1 is a basis. So is a basis means span of a V1 is equal to V. So by this result we can say that range of T is nothing but is equal to, we can say that span of T of V1 up to T of Vn and T of V of n plus 1 up to T of Vn. So this can be, by this result we can write this into this form. So this means RT we can write in this, but you know that because we have to assuming that Vi belongs to the kernel of a T, I running 1 to m. So we have a T of Vi is equal to, you have a 0 vector. So if it's 0 vector, then this up to this term is equal to, we have a 0. So but this is equal to 0 means we can say that the RT is nothing but is equal to span, because if we write a linear combination of span of this means these vectors can be written as a linear combination of the vectors of this, and because all T of Vi is equal to 0, then this linear combination can be written in the form of this. So this means RT is nothing but is equal to span of, you have a T of Vm plus 1 up to T of Vn, and if this is equal to this, then we can say that RT is nothing but is equal to span of A. So RT is nothing but is equal to span of A. This means this we have to prove that the first part of the this our consider case A is equal to this is a. So this we have to prove that first condition is proved, that span of A is equal to RT. Now next we show that this A is a linearly independent. If this is a linearly independent means we can write a linear combination of these vectors is equal to some 0 vector. So we can just start alpha m plus 1 up to this is a 0 vector, and now because of this we can say that this is a so T is a linear. By the linearity we can apply the linear, this is equal to 0 vector. Now this means if is 0 vector, this means we can say that alpha of m plus 1 V of m plus 1 and so on plus alpha n is belong to the kernel of a T. If this is the element of a kernel of a T, that means this is a element of a this is unique, and that is a unique representation means we can say that this can be any element in the kernel is linear combination of these vector is a unique. So this means this vector is in the belong to the kernel of a T. That means this vector can be written as a linear combination of the elements of the kernel of a T. So this means we can say that alpha of m plus 1 V of m plus 1 this can be written as a V of m plus 1 plus so on. We have a alpha n, Vn can be written as a beta 1 V1 beta 2 V2 up to we have a beta m and V beta m and we have a Vm. Now this can be written as the form of a, we have a beta 1 V1 plus beta 2 V2 and so on, plus we have a beta m Vm plus minus ka alpha m plus 1 V of m plus 1 plus minus ka f n plus 2 V of m plus 2 and so on, alpha minus ka minus alpha n Vn is equal to 0. Now this is the linear combination of the elements of a V1, V2, Vn, and this is the B1 as a basis, and then this is the element of a, you know that the B1 we have as the form of this V1, V2 up to Vm, Vm plus 1 up to we have a Vn. So this clearly we have this B1 is a linearly independent, If B1 is a linear independent, therefore this can be written as a linear combination of this is equal to 0 vector. So this implies that we can say that beta 1 is equal to you have a beta 2 and so on is equal to you have a beta m is equal to you have a alpha m plus 1 so on is equal to alpha n is equal to 0. So this means we can assuming all the show that is all the scalars are equal to 0. So this means this is by these equations we can say that all the scalars are equal to 0 means this is t of Vn plus 1, t of Vn plus 2 and up to t of Vn is a linearly independent. So this means if it is a linearly independent, then we can say that as clearly the dimension of this form a basis. So this means A over the set is form a so this is a unique linear combination for the basis for V of kernel of a T. So this means we can just say write into this form, or we just taking into this form is equal to 0. B1 is a being basis is a linearly independent. Therefore, all the scalars R is equal to you have a 0. So hence A is a linearly independent. Now, if A is a linearly independent means we can say that dimension of a RT is equal to n minus m is equal to dimension of a V. Dimension of RT, because A is you have to take a set in this form T of a V of m plus 1 up to T of Vn, and then number of element in this is equal to you have n minus m. So this gives this is the because this is a form as a basis of range of a T. This is a basis for RT. So in the dimension of a RT is nothing but a number of element in the basis is n minus m. So this is written n minus m, and this is nothing but is equal to we can say that this is n minus m. So this is equal to you can say that this is equal to V. So this is same is equal to V. N minus m is equal to you can get. So this is the dimension of a this is sorry this is plus. This is can be written as this is equal to minus, not equal. This is minus. We can say that dimension of a V minus dimension of a V kernel of, because we assuming that dimension of kernel of a T is equal to we have a m, and dimension of a V is equal to we have a n. So this n is a dimension of a V and m is a dimension of a kernel of a T. That means we can say that this is dimension of a kernel of a T and plus dimension of a range of a T is equal to n. This is also called because dimension of a kernel of a T we can say that nullity. So nt, and dimension of a range of a T also called is a rank. So it is RT, and this is equal to nothing but is equal to dimension of a V. We have to assume in this. So this complete the proof of the this theorem. This is called is the Rank-Nullity theorem, or we can also call this is a Sylvester law in other way. So now we have to discuss one more example based on this theorem. We try to verify this theorem by the example. So let we have to take a R4 to R3 be a linear map defined by TE1, TE2, TE3 in this form. So this is clearly we have a basis of a this B is equal to you have a E1, E2, E3, E4, and this is our standard basis. So this is a clearly is a basis. This is basis for R4, and these are the elements of this R3. So this means we can say that we can write any element of this is general. We can try to find the what is the general linear transformation of this. So we have a x1, x2, x3, x4. These are the element of a R4. Then this x1, x2, x3, x4 can be written as a x1 e1 plus x2 e2 plus x3 e3 plus x4 e4. Because x4 e4 I directly write because these are the standard basis. If we have to write x1, x2, this is the same is nothing but. Now we have to write a t of x1, x2, x3, x4 is equal to t of we have a x1 e1 plus x2 e2 plus x3 e3 x4 e4. Now t is we have a giving is a linear map, so we can use the linearity t of x1 t of e1 plus x2 t of e2 plus x3 t of e3 plus x4 t of e4. We can write into this form. Now we can substitute the value for e1, e2, e3. So in this case we can take in the form of x1, and then we have the rest of 1 1 1. So we have to write in the form x1 1 1 1 plus x2 you have a 1 minus 1 1 plus x3 you have a 1 0 0 plus x 4 you have 1 0 1, and then we have to simplify okay this and now clearly if you take first we take a RT. So RT is nothing but is equal to, we can say that in the form of the element of RT is in this form. So this is clearly write in the form of this. So we have to write E1 this is, and these are the 4 vectors, and this is the, we have a dimension of this is equal to 3. So every vectors of n plus 1 vectors is linearly dependent. So clear these 4 vectors are linearly dependent, then one of them, this can be written in the linear combination of any 2 of them. Thus we have a, this can be written in this form. So this can be clearly, these vectors can be excluding. Now we have to, these 3 vectors are here. Now span of these 3 vectors. Now we try to check is these 3 vectors are linearly independent or dependent. So we take alpha 1 times 1 1 1 plus alpha 2 times 1 minus 1 1 plus alpha 3 times 1 0 0 is equal to 0 0 0. So we have alpha 1 plus alpha 2 plus alpha 3 is equal to 0. You have alpha 1 minus alpha 2 is equal to 0. Then you have a alpha 1 plus alpha 2 is equal to 0. This implies that you have a alpha 1 is equal to 0. Then you have a, implies that you have a alpha 2 is equal to 0, then alpha 3 is equal to 0. That means these 3 vectors are linearly independent. If these 3 vectors are the linearly independent, they form a basis. So this form a basis for RT. So this means we can say that dimension of range of a T is nothing but equal to 3. So we have a dimension of a range of a T is equal to, we just said that these 3 vectors are clearly linearly independent. So if we have these 3 vectors are linearly independent, then dimension of a range of a T is clearly is equal to 3. Now we have to find the range kernel. Kernel we have to find, I just already explained you how you can write in this form. Then we have to operate the T. We have a x1 x2, okay, just leave this, T of x1 x2 x2, this is already adjusted into this form. Now because kernel of T is nothing but is equal to, you can say that V is the element of a V such that T of V is equal to 0. So by this definition, this quantity is equal to 0, and this is using the linearity condition. Now we have to using the T of E1 E2 E3 values of a T of E1 E2 E3. You know that a T of E1 is equal to, you have a 1 1 1, and then you have a somewhere is a T of E2 also you have a just check here, you have a 1 minus 1 1. So you have a T of E2 is equal to 1 minus 1 1, and then you have a T of E3, and similarly just check. So E3 is equal to, you have a I think so you have a 1, we have a 1 T of E3 is equal to, you have a this 1 0 0. So we have a, we can say that this is clearly you have a this is you have a 1 0 0, and T of E4 is equal to 1 0 1. So substituting value from here, so you have a x1 plus x2 plus x3 plus x4. Now we have a x1 minus x2, x1 minus x2 only. Then we have a x1 plus x1 plus x2 plus x4 are there. Now if we have to just this, we have x1 plus x2 plus x3 plus we have a x4 is equal to 0, and the second is equal to x1 is equal to, you have a x2, and then we have a x4 is equal to, you have a minus ka x1 minus ka x2, and x1 is equal to, you have a x2. So you have a minus ka twice x2. So x4 is equal to, you have a minus ka twice x2. So now we have a substitute here. So you have a twice x1 twice x2 plus x3. We can just say this is okay, x3. Now minus ka twice x2 is equal to 0. That way x3 is equal to 0. So this means we have a kernel is the element of this type. So we can say that the kernel of the element of this type. So, this means we have to simplify this, we have to getting this x1, x2, x3 is equal to this, because x1 is equal to x2, and we have to just say that x2 is equal to, you have a minus ka x4 is equal to minus ka twice x2, or so x2 is equal to minus ka x4 by 2. Directly you can just say that, then we can just say that kernel of a t is the form of a, you have to x1, x2, x1 is equal to, you have a x1, x2, x3 are the same, and then either you just write a x1 is equal to x2 is equal to x4 minus by 2. So, we can just write as a x2, then you have a x2 0, and then we have a minus ka twice x2, and then we have a such that we have a x2 is the element of R. Then kernel of a t is nothing but is equal to, you have to just say that 1 1 0 minus 2. This is the span of a, we can say that like this, span of 1 1 0 and minus 2, and this is clearly is a linearly independent, and so that we can just say that the dimension of kernel of t is equal to, you have a 1. And now we have a t from R4 to R3 map, and then we have a show that the dimension of kernel of a t is equal to 1, and dimension of range of a t is equal to 3. So, we have to take this dimension of kernel of a t plus dimension of range of a t is equal to we have to just say that is equal to, we can say that 1 plus 3 is equal to 4 is the same as the dimension of a R4. So, this means we can just say that into this form. So, this is clearly we have to verify that the theorem is this theorem is verified. So, this complete we have to complete the proof of the theorem, and also we have to verify this theorem by this example. Okay, now I have to stop this class today here, and in the next class we have to discuss about the 1 1 and on 2 linear transformations, and we have a how to find a linear transformation is a 1 1, and if we have a some basic result based on the linear transformation, and by use this application of this theorem, by the help of this theorem we can see how can use this theorem in as a application of finding the 1 1 on 2 linear transformation. Thank you very much for this class.